Tonight, as you gaze up at the endless expanse of stars scattered across the cosmic darkness, you're witnessing something far more profound than a simple collection of distant lights. You're looking at the universe in the middle of its story, a story that began nearly 14 billion years ago with the most spectacular explosion ever conceived, and one that might not have an ending at all. What if everything we know about cosmic death is wrong? What if the universe doesn't simply fade into cold, empty darkness, but instead finds a way to begin again? What if the Big Bang that started everything wasn't actually a beginning, but just the latest chapter in an endless cycle of cosmic death and rebirth? Welcome to a journey through the deepest mysteries of existence itself, where cutting-edge physics meets ancient questions about eternity, where the most brilliant minds in cosmology are discovering that our universe might be far stranger and more resilient than we ever imagined. Before we dive into this cosmic odyssey together, I'd love to know where you're joining me from tonight, and what keeps you awake wondering about our place in this vast cosmos. If you find yourself drawn to these profound questions about existence, I'd be grateful if you joined our community of cosmic explorers with a like and perhaps a subscription. Get ready. The journey begins now. To understand whether the universe can truly die and be reborn, we must first confront the most unsettling prediction in all of cosmology: the heat death of the universe. This isn't some distant theoretical concern for scientists to debate in ivory towers. This is the ultimate fate that current physics predicts for everything that has ever existed or ever will exist. Picture this scenario unfolding across incomprehensible spans of time. In roughly 100 trillion years, the last stars will flicker out of existence. The universe will have expanded so dramatically that galaxies will be separated by distances that make current cosmic voids seem crowded. The temperature everywhere will drop to just a fraction of a degree above absolute zero. But this is only the beginning of the end. As we push forward through timescales that make the current age of the universe seem like a single heartbeat, even more dramatic changes await. Black holes, those cosmic monsters that devour everything in their vicinity, will begin to evaporate through a process called Hawking radiation. The supermassive black holes at the centers of galaxies will persist the longest, but even they cannot escape this fate. After roughly 10 to the 100th power years, every black hole in the universe will have vanished, leaving behind only elementary particles scattered across an exponentially expanding void. This is heat death. Not a fiery conclusion, but the coldest, loneliest ending imaginable. A universe where no energy differences exist to power any processes, where entropy has reached its maximum possible value, where nothing interesting can ever happen again. The cosmos reaches what physicists call thermodynamic equilibrium, a state of perfect, eternal boredom. But here's what should make your mind reel with possibility. Some of the most brilliant theoretical physicists alive today are suggesting this might not be the end at all. They're proposing that the universe has mechanisms built into its very fabric that could allow it to restart, to bounce back, to begin the entire cosmic story over again. The first hint that our universe might be more resilient than heat death suggests comes from quantum mechanics itself. Even in the deepest possible emptiness, quantum field fluctuations ensure that space is never truly empty. Virtual particles pop into existence and annihilate each other in timeframes so brief they seem instantaneous. But quantum mechanics also tells us that, given enough time, truly astronomical amounts of time, these fluctuations could theoretically create something far more dramatic. Consider the mathematics of probability across infinite time. In roughly 10 to the 10 to the 56th power years, quantum fluctuations could spontaneously create a region of space with enough energy density to undergo cosmic inflation. This would essentially birth a new Big Bang, creating an entirely fresh universe from the quantum vacuum itself. The probability is unimaginably small, but infinity provides unlimited opportunities for even the most unlikely events to occur. This quantum resurrection represents just one pathway the universe might take to avoid eternal death. But there are others, and they're grounded in some of the most sophisticated physics humanity has ever developed. Enter the realm of cyclic cosmology, where the universe doesn't die once but lives and dies repeatedly across endless cycles. These aren't wild speculations, but serious theoretical models developed by leading cosmologists using the mathematics of general relativity and quantum field theory. The most elegant of these proposals comes from Roger Penrose, the Nobel Prize-winning physicist whose contributions to our understanding of black holes and space-time are legendary. His theory, called conformal cyclic cosmology, suggests that our universe is just one episode in an infinite sequence of cosmic eons, each beginning with a big bang and ending with something far more subtle than a big crunch. In Penrose's model, the universe doesn't need to collapse back on itself to restart. Instead, the far future of our expanding cosmos, when all matter has been processed through stellar evolution and all black holes have evaporated away, becomes mathematically identical to the conditions of a new Big Bang. Through the magic of conformal geometry, the infinite future of one cosmic cycle connects seamlessly to the birth of the next. The mechanism is breathtakingly elegant. Black holes, which represent the universe's most efficient entropy-gathering systems, slowly evaporate through Hawking radiation over periods so vast they make geological time seem instantaneous. As these cosmic vacuum cleaners disappear, they take with them enormous quantities of entropy, gradually returning the universe to a state of smooth, low-entropy uniformity, reminiscent of the early Big Bang. When the last black hole finally evaporates, space becomes populated only by massless particles, photons, and possibly neutrinos, traveling through an ever-expanding void. In this far-future epoch, the concept of scale loses its meaning. Without massive particles to provide reference points, the universe can undergo what mathematicians call a conformal transformation, essentially resetting its scale and beginning a new cycle of cosmic evolution. But Penrose's model faces significant challenges. Critics point out that the theory requires very specific conditions to work, conditions that may not actually occur in our universe. The model depends crucially on the complete evaporation of all black holes, but some theoretical work suggests that certain types of black holes might be stable against Hawking radiation. If even a single black hole persists into the far future, the conformal transition cannot occur. Moreover, the observational evidence for conformal cyclic cosmology remains controversial. Penrose and his collaborators have claimed to identify signatures of previous cosmic cycles in the cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space. They point to circular patterns and hotspots that they argue represent the gravitational wave signatures of colliding black holes from previous eons, somehow transmitted across the boundary between cosmic cycles. However, multiple independent analyses of the same data have failed to confirm these claimed detections. The statistical significance of the purported evidence has been disputed, with most cosmologists concluding that the patterns Penrose identifies are consistent with random fluctuations in the cosmic microwave background rather than genuine signals from previous universes. This scientific disagreement highlights a fundamental challenge in cyclic cosmology. Unlike other areas of physics where we can design experiments to test theories, the timescales involved in cosmic cycles are so vast that direct observation seems impossible. We must rely on subtle, indirect signatures and mathematical consistency to evaluate these proposals. Yet the mathematical beauty of cyclic models continues to attract serious attention from theoretical physicists. Alternative approaches to cosmic recycling have emerged from string theory, loop quantum cosmology, and other cutting-edge frameworks for understanding the fundamental nature of space and time. String theory, which attempts to describe all fundamental particles as vibrating strings in higher dimensional space, naturally gives rise to scenarios where universes can collide and bounce off each other. In these brain cosmology models, our three-dimensional universe exists as a membrane floating in a higher dimensional space. When two such brains collide, the enormous energies released could trigger a new Big Bang, creating a fresh cosmos from the ashes of previous ones. The mathematical framework of string theory allows for incredibly rich dynamics in these higher dimensions. Brains can oscillate, collide, separate, and merge in complex patterns that could generate not just one recycling event, but an entire ecosystem of interacting universes. Each collision would reset the physical conditions in the affected brains, potentially giving rise to universes with different physical constants, different numbers of dimensions, or entirely different laws of physics. Meanwhile, loop quantum cosmology, which applies the principles of quantum mechanics to the geometry of spacetime itself, suggests that the Big Bang's singularity might not represent the true beginning of the universe, but rather a quantum bounce from a previous contracting phase. In this framework, space and time are not smooth and continuous, but composed of discrete, quantized units at the smallest scales. When a contracting universe reaches the maximum density that quantized spacetime can support, roughly the Planck density, quantum effects become dominant and cause the collapse to reverse into expansion. This creates a big bounce rather than a Big Bang, transforming what appeared to be a cosmic death into a cosmic resurrection. The loop quantum cosmology approach addresses one of the most troubling aspects of traditional Big Bang theory: the initial singularity, where physical laws break down and meaningful predictions become impossible. By replacing the singularity with a quantum bounce, the theory provides a natural mechanism for cosmic recycling that doesn't require exotic physics or higher dimensions. Computer simulations of loop quantum cosmology have shown that universes can indeed bounce from contraction to expansion, while preserving enough information from the previous cycle to potentially explain features we observe in our current cosmos. The quantum geometry that underlies spacetime in this theory acts as a cosmic trampoline, preventing complete gravitational collapse and enabling the universe to spring back into a new phase of expansion. But even these sophisticated quantum approaches to cosmic recycling face formidable challenges. The second law of thermodynamics, which states that entropy always increases in isolated systems, presents a fundamental obstacle to any cyclic model. Each cycle would naturally accumulate more disorder than the previous one, gradually degrading the universe's ability to organize itself into complex structures. Traditional cyclic models failed precisely because they couldn't explain how entropy could be reset between cycles. If the universe simply oscillated between expansion and contraction, each cycle would be less organized than the last, eventually leading to a heat death scenario despite the cosmic recycling. Modern cyclic theories attempt to address this entropy problem through various mechanisms. Some propose that the expansion phase of each cycle stretches space so dramatically that entropy gets diluted to negligible levels, essentially resetting the cosmic disorder. Others suggest that the fundamental laws of physics themselves might change between cycles, allowing entropy to be processed or eliminated in ways that aren't possible within a single cosmic epoch. The stakes in this debate couldn't be higher. If the universe truly dies a heat death with no possibility of renewal, then consciousness, creativity, and everything we consider meaningful will eventually vanish forever. The cosmos will become a cold, empty void where nothing interesting can ever happen again. But if cyclic models are correct, then our universe participates in an eternal dance of death and rebirth, where each ending becomes a new beginning. The implications extend far beyond academic cosmology into the deepest questions about meaning and purpose in existence. Are we living in a unique, irreplaceable cosmos that will eventually fade into oblivion? Or are we part of an eternal cycle where consciousness and complexity can emerge again and again across infinite time? Recent observations have added new wrinkles to this cosmic mystery. The discovery that our universe's expansion is accelerating, driven by the mysterious dark energy that comprises roughly 70% of all cosmic content, has profound implications for the ultimate fate of space and time. If dark energy maintains its current properties indefinitely, it will drive the expansion to accelerate exponentially, making any future contraction or recycling seem impossible. But we understand remarkably little about dark energy's true nature. Current observations are consistent with it being a cosmological constant, an unchanging property of empty space itself. However, alternative models suggest that dark energy might evolve over cosmic time, potentially weakening enough to allow gravitational attraction to eventually overcome cosmic expansion. If dark energy proves to be dynamic rather than constant, entirely new possibilities open up for the universe's long-term fate. A weakening dark energy could allow the cosmos to eventually stop expanding and begin contracting, setting the stage for either a big crunch or a big bounce, depending on the quantum properties of spacetime at extreme densities. Conversely, a strengthening dark energy could lead to an even more dramatic finale than simple heat death. In what cosmologists call the Big Rip scenario, dark energy would become so powerful that it eventually overcomes not just gravitational attraction between galaxies, but the fundamental forces that hold atoms together. Space itself would expand so rapidly that molecular bonds would snap, atomic nuclei would disintegrate, and even subatomic particles would be torn apart in a cosmic crescendo of destruction. The Big Rip represents perhaps the most definitive ending imaginable for our universe. Unlike heat death, which leaves behind a cold but stable cosmos of elementary particles, the Big Rip would literally shred the fabric of reality itself. No recycling mechanism could survive such complete annihilation of space and time. If this scenario proves correct, our universe is racing toward an appointment with absolute nothingness in roughly 22 billion years. Yet even here, at the edge of cosmic oblivion, quantum mechanics whispers possibilities that challenge our intuitions about endings. The mathematics of quantum field theory suggest that even the complete destruction of spacetime might not represent a true termination. Virtual particles and quantum fluctuations operate according to principles that transcend classical notions of existence and non-existence. In the quantum realm, something can emerge from nothing, and the very concept of absolute emptiness becomes meaningless. This brings us to one of the most mind-bending proposals in modern cosmology: the idea that our universe might not be alone, but part of an infinite multiverse where cosmic births and deaths occur continuously across vast regions of higher dimensional space. In eternal inflation theory, the Big Bang that created our observable universe was just one bubble of expansion in an endless sea of cosmic creation. According to this model, quantum fluctuations in a primordial scalar field, called the inflaton, create regions where space undergoes exponential expansion, giving birth to pocket universes like our own. Each bubble universe experiences its own Big Bang, develops its own physical laws, and follows its own evolutionary trajectory toward whatever ultimate fate its particular physics dictates. The beauty of eternal inflation lies in its mathematical inevitability. Once inflation begins anywhere in this higher dimensional space, it continues forever, constantly spawning new universes, while existing ones evolve and potentially die. Our universe becomes just one leaf on an infinite tree of cosmic creation, where birth and death operate simultaneously across scales that dwarf even our expanded conception of cosmic vastness. In this framework, the question of whether our particular universe dies and restarts becomes almost irrelevant. Even if our local cosmos suffers heat death, Big Rip, or any other terminal fate, the eternal inflation process ensures that countless other universes continue the story of cosmic evolution. Somewhere in this infinite multiverse, universes identical to ours go through their own cycles of stellar birth, galactic evolution, and ultimate endings. But eternal inflation raises profound questions about the nature of existence itself. If infinite universes with every possible variation of physical laws are constantly being created, what makes our particular cosmos special or meaningful? Are we living in just one temporary bubble in an endless ocean of cosmic possibilities? The mathematics of eternal inflation also suggests something even more startling. Given infinite time and infinite space, every possible configuration of matter and energy will eventually occur somewhere in the multiverse. This includes perfect copies of our observable universe, complete duplicates of Earth, and identical versions of every person who has ever lived. In an infinite multiverse, not only does the universe restart, but it recreates every possible version of itself infinitely many times. This leads to the ultimate puzzle in cosmic recycling, the measure problem. In an infinite multiverse where everything possible happens infinitely often, how do we calculate probabilities or make predictions? Traditional physics relies on comparing the likelihood of different outcomes, but when all outcomes occur infinitely often, the mathematical framework breaks down. Some cosmologists have proposed that the solution lies in understanding the quantum mechanics of cosmic creation itself. Recent developments in quantum cosmology suggest that the birth of universes might not be random events, but governed by deeper principles that determine which types of cosmos are more likely to form and persist. The quantum genesis model, developed by theoretical physicist Narman Kumar, proposes that universes are created in pairs, with each cosmos accompanied by an anti-universe with opposite properties. This symmetric creation process could explain mysterious features of our own universe, including the nature of dark matter and dark energy, while providing a mechanism for cosmic recycling that operates through quantum entanglement across cosmic scales. In Kumar's model, our universe and its anti-universe remain quantum mechanically connected, even as they evolve separately. The accelerating expansion we observe, driven by dark energy, might actually result from this quantum entanglement gradually strengthening over cosmic time. As the connection intensifies, it could eventually trigger a phase transition that resets both universes to their initial low entropy states, beginning new cycles of cosmic evolution. This quantum approach to cosmic recycling avoids many of the problems that plague classical cyclic models. Instead of requiring the universe to physically contract and re-expand, the reset occurs through quantum mechanical processes that can operate even during continued expansion. The entropy problem that doomed earlier cyclic theories gets solved through the symmetric creation mechanism, which allows disorder to be transferred between universe and anti-universe pairs. Yet for all its mathematical elegance, quantum cosmology operates in realms so far removed from direct observation that testing these ideas poses extraordinary challenges. The quantum processes that supposedly govern cosmic creation occur at energy scales trillions of times higher than anything we can produce in particle accelerators. The timescales involved in cosmic recycling extend far beyond the current age of our universe. This observational challenge has led some physicists to explore whether the fundamental structure of spacetime itself might preserve evidence of previous cosmic cycles or parallel universes. Loop quantum gravity, which treats space and time as composed of discrete quantized units at the smallest scales, suggests that information might be preserved across cosmic bounces in ways that classical general relativity cannot accommodate. In loop quantum cosmology, the Big Bang emerges not from a singular point of infinite density, but from a quantum bounce that occurs when a previous universe reaches maximum compression. The discrete structure of quantum spacetime prevents the formation of true singularities, ensuring that information about the previous cosmic cycle gets encoded in the quantum geometry itself. Computer simulations based on loop quantum gravity have shown that these quantum bounces can preserve surprisingly detailed information about the previous universe, including the seeds of large-scale structure that eventually grow into galaxies and galaxy clusters. This raises the tantalizing possibility that our current cosmos might contain fossil evidence of whatever universe preceded it. The search for such evidence has become one of the most exciting frontiers in observational cosmology. Researchers are analyzing the cosmic microwave background radiation with unprecedented precision, looking for subtle patterns that might reveal the signature of quantum bounces or the gravitational wave echoes of cosmic recycling events. Some scientists have claimed to identify anomalous features in the cosmic microwave background that could represent evidence of previous cosmic cycles. These include concentric rings of temperature variations that might result from gravitational waves generated during the collision of supermassive black holes in a previous eon, and hotspots that could mark the final moments of black hole evaporation before conformal recycling. However, the statistical significance of these claimed detections remains highly controversial. Multiple independent analyses have failed to confirm that these patterns represent genuine signals rather than random fluctuations in the cosmic background radiation. The extraordinary nature of the claims requires equally extraordinary evidence, and the current data falls short of that standard. This uncertainty reflects a deeper challenge in cosmology, distinguishing between genuine physical processes and the human tendency to see meaningful patterns in random data. When we're searching for evidence of cosmic events that occur once every 100 billion years, we must be extraordinarily careful not to mistake noise for signal. The debate over cosmic recycling has also revealed fundamental tensions between different approaches to theoretical physics. String theorists, who work with mathematical frameworks involving extra dimensions and exotic particles, tend to favor models where universes can interact and influence each other across higher dimensional space. Loop quantum gravity researchers, focused on the discrete structure of spacetime at quantum scales, prefer scenarios where recycling occurs through quantum mechanical processes within our existing four-dimensional universe. These different approaches make dramatically different predictions about what evidence of cosmic recycling we might hope to detect. String theory models involving brane collisions would likely leave signatures in the polarization patterns of the cosmic microwave background, while loop quantum cosmology bounces might be detectable through their effects on primordial gravitational waves. Meanwhile, the conformal cyclic cosmology proposed by Roger Penrose operates through mathematical transformations that could erase most evidence of previous cycles, making observational confirmation extraordinarily difficult. This creates a frustrating situation where some of the most elegant recycling mechanisms are also the least testable. The question of cosmic recycling has also forced physicists to confront deep philosophical issues about the nature of time and causality. If the universe truly undergoes infinite cycles of death and rebirth, what does it mean to speak of a beginning or end to cosmic history? Are we living in a unique moment within an eternal cycle, or just one iteration in an infinite sequence of identical or nearly identical universes? These questions become even more complex when we consider the role of consciousness and observation in quantum mechanics. Some interpretations of quantum theory suggest that conscious observers play a fundamental role in determining physical reality. If this is true, does the presence of intelligent life in the universe somehow influence whether cosmic recycling occurs? The anthropic principle, which attempts to explain why our universe seems fine-tuned for the existence of complex structures and conscious observers, takes on new dimensions in recycling cosmologies. If the universe undergoes infinite cycles, each with potentially different physical constants and laws, then conscious observers would naturally find themselves in cycles where the physics permits their existence. This could explain why our universe appears so precisely calibrated for star formation, chemical complexity, and biological evolution. We observe these favorable conditions not because they're objectively special, but because conscious observers can only exist in cosmic cycles where such conditions prevail. Yet this anthropic reasoning leads to troubling implications for the future of consciousness in our universe. If recycling mechanisms depend on the complete evaporation of black holes and the elimination of all complex structures, then conscious observers cannot survive the transition between cosmic cycles. Each recycling event would effectively reset not just the physical universe, but the possibility for awareness and understanding. This creates a cosmic tragedy where consciousness represents a temporary flowering of the universe's capacity for self-understanding, destined to be extinguished and forgotten with each recycling event. We become transient patterns of matter and energy that briefly achieve awareness before being swept away by the inexorable processes that renew the cosmos. However, some theoretical frameworks suggest more optimistic possibilities. If consciousness can somehow transcend its physical substrate through quantum mechanical processes we don't yet understand, it might persist across cosmic cycles in forms that bear little resemblance to biological intelligence. The information patterns that constitute conscious experience could potentially survive recycling events encoded in the quantum structure of space-time itself. The search for cosmic recycling has thus become more than an academic exercise in theoretical physics. It represents humanity's attempt to understand whether consciousness and meaning can persist on truly cosmic scales, or whether we are temporary phenomena destined for ultimate extinction, regardless of whether the universe itself finds ways to renew and continue. As we probe deeper into these questions, we find ourselves at the intersection of physics and metaphysics, where the hardest mathematical equations meet the deepest human concerns about mortality and meaning. The universe's potential for death and rebirth mirrors our own existential struggles, projected onto scales so vast they challenge our capacity for comprehension. The evidence for these cosmic recycling mechanisms remains tantalizingly elusive, scattered across mathematical equations that describe physics at scales where our normal intuitions completely break down. We're attempting to understand processes that operate across time periods so vast that the entire history of human civilization represents less than a single tick of the cosmic clock. Consider the mathematical foundations underlying these recycling theories. Einstein's field equations, which govern the curvature of spacetime, become extraordinarily complex when applied to the universe as a whole. The solutions describe not just how space expands or contracts, but how the very geometry of reality can transform in ways that challenge our deepest assumptions about existence itself. In the framework of general relativity, spacetime is not a fixed stage upon which cosmic drama unfolds, but a dynamic participant that can stretch, compress, and even topology change in response to the matter and energy it contains. This mathematical flexibility provides the theoretical foundation for cosmic recycling, allowing physicists to construct models where the apparent end of one universe becomes the beginning of another through purely geometric transformations. The Friedmann equations, which describe how the universe's expansion rate depends on its energy content, reveal something profound about cosmic destiny. These equations show that the ultimate fate of spacetime depends critically on the balance between matter, radiation, and the mysterious dark energy that currently drives accelerated expansion. Small changes in this cosmic recipe can lead to dramatically different endings. When cosmologists input the observed values for dark energy density, matter content, and expansion rate into these equations, They find that our universe sits precariously close to several critical thresholds. We appear to live in a cosmos balanced on the knife's edge between different possible futures, where tiny variations in fundamental parameters could tip us toward a heat death, big rip, or something entirely unexpected. But the mathematics of cosmic recycling extends far beyond Einstein's classical theory into the quantum realm, where space and time themselves become subject to the uncertainty principle. Quantum field theory in curved space-time reveals that even empty space teems with virtual particles that pop into existence and vanish on timescales too brief to measure directly. These quantum fluctuations become amplified in extreme gravitational fields, leading to phenomena like Hawking radiation from black holes. Stephen Hawking's calculations showed that black holes gradually evaporate by emitting thermal radiation, slowly converting their mass into energy that escapes to infinity. This process provides a mechanism for the universe to cleanse itself of entropy-rich regions, gradually returning to a state of smooth uniformity. The mathematics of Hawking radiation reveals something extraordinary about information and entropy in cosmic recycling. When a black hole evaporates completely, it appears to take with it all information about the matter that originally formed it. This creates what physicists call the information paradox, a fundamental conflict between quantum mechanics and general relativity that remains unresolved after decades of intense research. Some proposed solutions to this paradox have profound implications for cosmic recycling. If information is somehow preserved during black hole evaporation, perhaps encoded in subtle correlations in the Hawking radiation, then the universe might retain memory of its previous states even after apparent reset events. The quantum information that describes our current cosmos could survive recycling processes, influencing the structure and evolution of subsequent cosmic cycles. The holographic principle, emerging from string theory and quantum gravity research, suggests that all information in a volume of space can be encoded on its boundary. This mathematical insight implies that the three-dimensional reality we experience might actually be a projection from information stored on a two-dimensional surface, similar to how a hologram creates the illusion of depth from patterns on a flat screen. Applied to cosmic recycling, holographic encoding could allow information about entire universes to be preserved in the quantum geometry of space-time boundaries. Even if the interior of a cosmic cycle undergoes complete thermal equilibrium, the boundary conditions might retain sufficient information to seed the structure of subsequent cycles. String theory provides another mathematical framework for understanding cosmic recycling through its description of fundamental particles as vibrating strings in higher dimensional space. The equations of string theory naturally incorporate gravity along with the other fundamental forces, potentially resolving the mathematical incompatibilities that plague attempts to combine quantum mechanics with general relativity. In string cosmology, our three-dimensional universe exists as a brane, a membrane-like object floating in a higher dimensional space called the bulk. Multiple branes can coexist in this bulk, potentially colliding with each other in events that release enormous energies. These brane collisions could trigger new Big Bang events while preserving the overall structure of the higher dimensional space. The mathematical description of brane dynamics reveals rich possibilities for cosmic recycling that extend far beyond simple expansion and contraction cycles. Branes can oscillate, rotate, merge, and separate in complex patterns that could generate not just periodic recycling, but chaotic sequences of cosmic creation and destruction operating across multiple timescales simultaneously. Loop quantum gravity approaches cosmic recycling from a fundamentally different mathematical perspective, treating space and time as composed of discrete, quantized units at the smallest scales. In this framework, the smooth spacetime of general relativity emerges as an approximation valid only at scales much larger than the Planck length, roughly 10 to the minus 35 meters. The discrete structure of loop quantum spacetime prevents the formation of true singularities, replacing them with quantum bounces where extreme compression gives way to expansion. The mathematics of these bounces shows that they can preserve detailed information about the previous cosmic cycle, encoding the seeds of future structure in the quantum geometry itself. Computer simulations based on loop quantum gravity have demonstrated that universes can indeed bounce from contraction to expansion, while maintaining enough memory of their previous state to explain observed features of our cosmos. The quantum mechanical evolution of spacetime geometry acts as a cosmic memory bank, storing information across bounce events in ways that classical physics cannot accommodate. These mathematical frameworks converge on a remarkable conclusion. The universe might possess multiple pathways for renewal that operate through different physical mechanisms. Conformal recycling through geometry, quantum tunneling through vacuum states, brane collisions in higher dimensions, and quantum bounces in discrete spacetime all represent mathematically consistent routes from cosmic death to cosmic rebirth. Yet translating these mathematical possibilities into observational predictions remains extraordinarily challenging. The energy scales involved in cosmic recycling processes exceed anything we can probe directly by factors of trillions. The timescales stretch across periods so vast that direct observation seems fundamentally impossible given the finite age and future lifetime of any conceivable civilization. This observational challenge has forced cosmologists to develop increasingly sophisticated, indirect methods for testing recycling theories. They search for fossil evidence of previous cycles encoded in the cosmic microwave background radiation, analyze the statistical properties of large-scale structure formation, and probe the quantum vacuum for signatures of non-trivial topology that might indicate connections to other cosmic cycles. The Planck satellite mission has mapped the cosmic microwave background with unprecedented precision, revealing temperature fluctuations that carry information about conditions in the early universe. These measurements provide our most direct window into cosmic history, potentially preserving evidence of whatever processes preceded the Big Bang. Some researchers claim to have identified anomalous patterns in this data that could represent signatures of cosmic recycling. Circular temperature patterns might indicate gravitational wave signatures from previous cosmic cycles. Statistical correlations between widely separated regions could reveal evidence of non-trivial spatial topology connecting our universe to previous iterations. However, the statistical significance of these claimed detections remains highly disputed. The human brain excels at perceiving meaningful patterns even in random data, a tendency that becomes particularly problematic when searching for extraordinary phenomena in noisy observations. Multiple independent analyses have failed to confirm the statistical significance of most claimed recycling signatures. The debate over these observations reflects deeper tensions within the cosmological community about the standards of evidence required for accepting revolutionary theories. Cosmic recycling represents such a fundamental departure from conventional understanding that it demands extraordinarily convincing observational support before gaining widespread acceptance. This evidential challenge has led some physicists to explore whether recycling theories make predictions about phenomena we can observe more directly. If our universe is part of an eternal cycle, it might retain subtle influences from previous iterations that manifest in currently observable physics. The fine-tuning of fundamental constants provides one avenue for such investigations. The masses of elementary particles, the strengths of fundamental forces, and other parameters of physics appear precisely calibrated to allow the formation of complex structures and conscious observers. This apparent fine-tuning could reflect selection effects operating across multiple cosmic cycles. If physical constants vary between recycling events, conscious observers would naturally find themselves in cycles where these parameters permit their existence. The anthropic selection mechanism could explain why our universe seems so precisely tuned for complexity without requiring intelligent design or extraordinary coincidence. Recent measurements of fundamental constants across cosmic time have revealed subtle variations that might support this interpretation. The fine structure constant which governs electromagnetic interactions appears to have changed slightly over the universe's history. These variations could represent drift toward attracting values that optimize the universe's capacity for generating complex structures. Dark energy measurements provide another potential window into cosmic recycling. The density of dark energy appears remarkably close to critical values that determine the universe's ultimate fate. Small changes in this parameter could shift our cosmos toward collapse, accelerated expansion, or more exotic endings. Some cyclic models predict that dark energy density should evolve in specific ways as the universe ages, potentially providing observable signatures of recycling mechanisms. If dark energy results from quantum entanglement with an anti-universe, as suggested by Kumar's quantum genesis model, its evolution might follow patterns that distinguish this scenario from simpler cosmological constant models. The search for such evolutionary signatures has become a major focus of observational cosmology. Next generation dark energy surveys will measure the expansion history of the universe with unprecedented precision, potentially revealing whether dark energy truly remains constant or evolves according to patterns predicted by recycling theories. Gravitational wave astronomy opens yet another observational window into cosmic recycling. The ripples in spacetime detected by instruments like LIGO and Virgo carry information about the most violent events in cosmic history. If recycling processes generate gravitational waves, these signals might propagate across cosmic cycles, providing direct evidence of previous universal iterations. The mathematics of gravitational wave propagation in recycling cosmologies reveals fascinating possibilities. Waves generated during brane collisions or quantum bounces could retain their coherence across cosmic transitions, allowing future civilizations to detect echoes of previous universes in the gravitational wave background. Current gravitational wave detectors lack the sensitivity to probe these ultra-low frequency signals, but planned space-based observatories might achieve the precision needed to search for recycling signatures. The European Space Agency's LISA mission and similar future projects could potentially detect gravitational wave memories of cosmic recycling events. Even if direct detection proves impossible, the absence of predicted signals could provide valuable constraints on recycling theories. If certain models predict gravitational wave signatures that we fail to observe, this non-detection would help narrow the range of viable cosmic recycling mechanisms. The quantum vacuum itself might preserve evidence of cosmic recycling through subtle modifications to the properties of empty space. If our universe emerged from a previous cosmic cycle through quantum tunneling or conformal transition, the vacuum state might retain memory of this process in the form of modified field correlations or altered symmetry properties. Precision tests of quantum field theory in curved spacetime could potentially detect these vacuum modifications. Experiments measuring the Casimir effect, which depends sensitively on vacuum fluctuations, might reveal anomalies that indicate non-trivial vacuum topology associated with cosmic recycling. The interplay between quantum mechanics and gravity in recycling scenarios generates predictions about the fundamental structure of spacetime that could be testable through high-precision experiments. If space and time are truly discrete at the Planck scale, as suggested by loop quantum gravity, this granularity might leave detectable signatures in the propagation of light and gravitational waves. These observational challenges highlight a profound limitation in our current scientific methodology. We're attempting to understand cosmic-scale phenomena using tools designed to probe much smaller systems over much shorter timescales. The extrapolation from laboratory physics to cosmic recycling requires leaps of faith that some scientists find uncomfortable. Critics of recycling theories argue that the mathematical elegance of these models provides insufficient justification for accepting such extraordinary claims without extraordinary evidence. They contend that the apparent fine-tuning of our universe could result from selection effects within a multiverse of random cosmic parameters requiring no recycling mechanism. The eternal inflation scenario provides an alternative explanation for cosmic fine-tuning that operates through spatial rather than temporal selection. If quantum fluctuations continuously create new regions of space with different physical parameters, conscious observers would naturally find themselves in regions where these parameters permit their existence. This spatial multiverse model makes dramatically different predictions than temporal recycling theories. Instead of cyclical repetition, eternal inflation predicts an infinitely branching tree of cosmic creation, where every possible universe exists simultaneously in different regions of space. The observational signatures of eternal inflation differ substantially from those predicted by recycling theories. Inflation models predict specific patterns in the cosmic microwave background that result from quantum fluctuations during the inflationary epoch. These predictions have been confirmed by multiple independent observations, providing strong support for the inflationary paradigm. However, eternal inflation faces its own theoretical challenges, particularly the measure problem that arises when attempting to calculate probabilities in an infinite multiverse. If every possible outcome occurs infinitely often across infinite space, traditional methods for making predictions break down completely. Some physicists have proposed that the resolution lies in understanding the quantum mechanics of cosmic creation itself. Recent developments in quantum cosmology suggest that universe creation might not be a random process, but governed by deeper principles that determine which types of cosmos are more likely to form and persist. The quantum genesis model represents one attempt to address these foundational issues by proposing that universes are created in symmetric pairs through quantum mechanical processes. This approach naturally resolves many of the mathematical pathologies that plague simpler creation models while making specific predictions about observable phenomena. If the quantum genesis framework proves correct, our universe's apparent fine-tuning results not from random chance or infinite repetition, but from fundamental symmetries in the quantum mechanical processes that govern cosmic creation. The relationship between universe and anti-universe pairs could determine the values of physical constants through entanglement effects that persist across cosmic evolution. These competing theoretical frameworks reflect deeper philosophical divisions within the physics community about the nature of scientific explanation itself. Some researchers prefer theories that make minimal assumptions about unobservable phenomena, even if this requires accepting apparently improbable coincidences in the observed universe. Others argue that the apparent fine-tuning of cosmic parameters demands explanation through mechanisms that transcend our local cosmic environment. Whether through temporal recycling, spatial multiverses, or quantum creation symmetries. The choice between these approaches often reflects underlying beliefs about the relationship between mathematics and physical reality. The debate has practical implications for the allocation of research resources and the direction of future investigations. Should we focus on developing more sensitive instruments to search for recycling signatures, or concentrate on understanding the quantum mechanics of cosmic creation through theoretical research and laboratory experiments? The answer may depend on which approach offers the most promising path toward resolving fundamental questions about the nature of existence itself. If cosmic recycling proves real, It would transform our understanding of time, causality, and the relationship between consciousness and cosmos. If recycling theories prove incorrect, this negative result would still provide valuable constraints on the possible mechanisms governing cosmic creation and evolution. Meanwhile, the mathematical development of recycling theories continues to reveal new possibilities and refine existing predictions. Advanced computer simulations of quantum gravity effects, string theory dynamics, and cosmic evolution provide increasingly detailed models of how recycling processes might operate. These theoretical advances have identified several key observational tests that could distinguish between different recycling mechanisms. The patterns of gravitational wave generation, the evolution of dark energy density, and the statistical properties of cosmic structure formation all depend sensitively on which recycling process, if any, operates in our universe. The next decade promises to bring unprecedented observational capabilities that could finally resolve these questions. Next-generation cosmic microwave background experiments will probe temperature and polarization patterns with sensitivity approaching fundamental limits. Advanced gravitational wave detectors will explore frequency ranges where recycling signatures might be detectable. Most importantly, the James Webb Space Telescope and its successors will observe the early universe with clarity that could reveal direct evidence of whatever processes preceded the Big Bang. If cosmic recycling leaves observable traces, these instruments may finally provide the evidence needed to distinguish between competing theories. The implications of resolving the cosmic recycling question extend far beyond academic cosmology. Understanding whether the universe dies and restarts would fundamentally alter human perspectives on meaning, purpose, and the significance of conscious existence within cosmic history. If recycling proves real, consciousness becomes part of an eternal cosmic story where death represents transformation rather than termination. The patterns of thought and experience that constitute our inner lives would participate in processes that transcend individual mortality, connecting us to infinite cycles of cosmic creativity. If recycling proves false, consciousness emerges as a temporary flowering of complexity destined for ultimate extinction when the universe reaches its final equilibrium state. This perspective demands that we find meaning and purpose within the finite span of cosmic evolution, accepting that all achievements of intelligence will eventually vanish forever. The scientific resolution of these questions thus carries profound implications for human culture, philosophy, and the frameworks through which we understand our place in existence. We stand at a unique moment in cosmic history where our observational capabilities are approaching the precision needed to answer fundamental questions about the nature of time, space, and the ultimate fate of reality itself. Fate of reality itself. The search for answers to cosmic recycling has revealed something profound about the nature of scientific inquiry itself. We're probing questions that exist at the absolute frontier of human understanding, where the tools of mathematics and observation strain against the fundamental limits of what finite beings can comprehend about infinite processes. The vacuum decay scenario represents perhaps the most unsettling possibility in all of cosmology, not because of its violence, but because of its subtlety. Our universe might exist in what physicists call a metastable state, like a ball balanced precariously on the rim of a bowl, stable for now, but vulnerable to the slightest disturbance that could send it tumbling toward a fundamentally different configuration. The Higgs field, which gives mass to all particles in our universe, might not occupy its lowest possible energy state. Recent measurements of the Higgs boson mass at the Large Hadron Collider have placed our cosmos uncomfortably close to the boundary between stability and instability. The precise values we observe suggest we live in a universe balanced on a knife's edge between eternal persistence and catastrophic transformation. If a random quantum fluctuation somewhere in space triggers a transition, to the true vacuum state, a bubble of altered physics would expand outward at the speed of light, rewriting the laws of nature as it grows. Inside this bubble, particles might have different masses, forces might operate with altered strengths, and the very possibility of complex chemistry could vanish entirely. This bubble would be invisible until it reached you. The wall of true vacuum would arrive without warning, traveling at light speed, carrying with it a universe where the familiar architecture of atoms and molecules simply cannot exist. Everything you've ever known would be instantaneously transformed into configurations of matter governed by alien physics. Yet even this apocalyptic scenario might not represent the absolute end of cosmic possibility. The mathematics of quantum field theory suggest that vacuum decay could itself be part of a larger cycle where universes tunnel between different vacuum states across vast reaches of time. What appears to be ultimate destruction from our perspective might be cosmic renewal from a broader viewpoint. The anthropic principle takes on new dimensions when applied to vacuum transitions. If the multiverse contains regions with every possible vacuum configuration, conscious observers would naturally find themselves in bubbles where the physics permits their existence. We observe a metastable universe not because such configurations are objectively special, but because stable vacuum states might not support the complex chemistry required for awareness. This reasoning suggests that vacuum decay events might be essential features of cosmic evolution rather than catastrophic accidents. The transition between different vacuum states could serve as a mechanism for exploring the landscape of possible physics, gradually selecting configurations that optimize the universe's capacity for generating complexity and consciousness. String theory provides a mathematical framework for understanding this vacuum landscape through its description of the extra dimensions that might exist beyond our familiar 3 dimensions of space. In string cosmology, the apparent constants of physics result from the particular way these extra dimensions are compactified or curled up at scales too small to observe directly. The energy associated with different compactification schemes creates a vast landscape of possible vacuum states, each corresponding to a universe with different physical laws. Transitions between these vacua could occur through quantum tunneling processes that effectively reset the fundamental parameters governing cosmic evolution. The string landscape contains an enormous number of possible vacuum configurations, estimated at 10 to the 500th power or more distinct possibilities. Each represents a potential universe with its own values for particle masses, force strengths, and other fundamental parameters. The overwhelming majority of these configurations would produce sterile universes incapable of supporting complex structures or conscious observers. This vast space of possibilities transforms our understanding of cosmic fine-tuning from a problem requiring explanation to a natural consequence of exploring all available options. If the universe can tunnel between different vacuum states over cosmic timescales, it would naturally spend more time in configurations that support long-lived, complex evolution. The tunneling rates between different vacuum states depend on the mathematical details of the string compactification, creating a complex network of transitions that could operate across multiple timescales simultaneously. Some transitions might occur rapidly on cosmic scales, while others require periods vastly longer than the current age of our universe. This temporal hierarchy of vacuum transitions suggests that cosmic recycling might operate through a nested structure of cycles within cycles. Our observable universe could be experiencing relatively rapid oscillations between closely related vacuum states, while participating in much slower transitions between fundamentally different physical regimes. The observational signatures of such nested cycling would be extraordinarily subtle, requiring precision measurements that push against the fundamental limits of what any conceivable instrument could achieve. We might be embedded in cosmic processes so vast and slow that their detection requires observational baselines extending across multiple generations of scientific civilization. Loop quantum cosmology offers a different perspective on cosmic cycling through its description of spacetime as fundamentally discrete rather than continuous. In this framework, the apparent smoothness of space and time emerges as an approximation valid only at scales much larger than the Planck length, where quantum gravitational effects become dominant. The discrete structure of quantum spacetime naturally prevents the formation of singularities, replacing them with quantum bounces, where extreme compression gives way to expansion. These bounces preserve information about the previous cosmic cycle through the quantum geometry of spacetime itself, encoding the seeds of future structure in ways that classical physics cannot accommodate. Computer simulations of loop quantum cosmology have revealed remarkable robustness in this information preservation mechanism. Even when universes undergo extreme compression approaching the Planck density, the quantum geometric degrees of freedom retain detailed memory of their previous configuration. This memory guides the subsequent expansion phase, ensuring that the post-bounce universe inherits structural features from its predecessor. The mathematical elegance of this mechanism lies in its automatic nature. Unlike classical cyclic models that require special initial conditions or fine-tuning to avoid entropy problems, quantum bounces naturally preserve and process information through the fundamental properties of quantum geometry. The discrete structure of spacetime acts as a cosmic memory bank that operates without external intervention. Recent developments in loop quantum cosmology have shown that these quantum bounces can occur not just in homogeneous simplified models, but in realistic universes with complex matter distributions and gravitational wave content. The quantum geometric effects that prevent singularity formation operate locally throughout spacetime, ensuring that bounces occur even in highly inhomogeneous cosmic configurations. This universality of quantum bouncing suggests that loop quantum cosmology might provide a complete resolution to the Big Bang singularity problem while naturally incorporating cosmic recycling. Every apparent cosmic beginning would actually represent a quantum transition from a previous contracting phase, creating an eternal sequence of bounces extending infinitely into the past and future. The observational consequences of this eternal bouncing sequence depend critically on how much information survives each transition. If quantum bounces preserve detailed structural information, successive cosmic cycles might exhibit strong correlations that could be detectable through precision cosmological observations. Alternatively, if the bouncing process gradually erases fine-scale information while preserving only large-scale features, the observable signatures of previous cycles might be limited to subtle statistical correlations in the cosmic microwave background or large-scale structure formation patterns. The holographic principle, emerging from black hole physics and string theory, provides yet another lens through which to view cosmic recycling. This principle suggests that all information in a volume of space can be encoded on its boundary, implying that three-dimensional reality might actually be a projection from information stored on a two-dimensional surface. Applied to cosmology, holographic encoding could allow information about entire cosmic cycles to be preserved in the quantum geometry of spacetime boundaries. Even if the interior of a cosmic volume undergoes complete thermalization or vacuum decay, the boundary conditions might retain sufficient information to seed the structure of subsequent cycles. The mathematics of holographic cosmology reveals fascinating possibilities for information preservation across cosmic transitions. The holographic principle naturally incorporates the maximum entropy bounds discovered in black hole physics, ensuring that information storage and retrieval processes respect fundamental thermodynamic limits. This entropy management becomes crucial for addressing the traditional objection to cyclic cosmologies based on the second law of thermodynamics. If holographic encoding allows entropy to be processed and redistributed rather than simply accumulated, cyclic models might avoid the gradual degradation that doomed earlier proposals. Recent work in holographic cosmology has shown that the information capacity of cosmic boundaries scales with area rather than volume, providing enormous storage potential for encoding the complete state of cosmic cycles. This scaling relationship ensures that even universes of arbitrary size can have their information holographically encoded in finite boundary regions. The retrieval of this encoded information during cosmic transitions would require physical processes operating at the intersection of quantum mechanics and gravity. The mathematical framework of holographic duality provides specific mechanisms for such information transfer operating through quantum entanglement networks that connect boundary and interior degrees of freedom. These entanglement networks could persist across cosmic transitions, providing quantum mechanical channels through which information about previous cycles influences the structure of subsequent iterations. The strength and character of these influences would depend on the detailed dynamics of the transition process, creating a rich space of possibilities for cosmic evolution. The emergence of quantum error correction in holographic systems adds another layer of sophistication to information preservation mechanisms. Just as quantum computers use error correction codes to maintain coherent information despite environmental noise, cosmic holographic systems might naturally implement error correction protocols that preserve essential information across multiple cycling events. This quantum error correction could explain how cosmic recycling manages to maintain structural coherence despite the enormous energies and complex dynamics involved in cosmic transitions. The holographic encoding would automatically protect crucial information patterns while allowing non-essential details to be gradually erased through thermodynamic processes. The interplay between quantum error correction and cosmic evolution suggests that recycling mechanisms might naturally optimize themselves over multiple cycles, gradually improving their ability to preserve and transmit information. This optimization process could drive cosmic evolution toward configurations that maximize the universe's capacity for complexity and consciousness. Such optimization dynamics would transform cosmic recycling from a passive repetition of similar cycles into an active learning process where each iteration builds upon the achievements of its predecessors. The universe would gradually discover more effective ways to organize matter and energy, leading to progressively more sophisticated expressions of cosmic creativity. The possibility of cosmic learning through recycling raises profound questions about the relationship between consciousness and cosmic evolution. If the universe can optimize its own structure through cycling processes, does this optimization naturally lead toward configurations that support conscious observers? Are we living in a cosmos that has learned to think about itself? These questions push beyond the boundaries of conventional physics into territories where science meets philosophy and metaphysics. The mathematical frameworks we use to describe cosmic recycling are sophisticated enough to model learning and optimization, but translating these formal properties into claims about cosmic consciousness requires extraordinary caution. Yet the mathematics itself remains compelling. Information theoretic analyses of cosmic recycling reveal that the universe possesses computational resources vastly exceeding any conceivable artificial system. If these resources can be organized through cycling processes, the resulting information processing capabilities would dwarf human intelligence by incomprehensible margins. The search for evidence of such cosmic optimization has become a subtle but important theme in modern observational cosmology. Researchers examine the statistical properties of cosmic structure formation, looking for patterns that might indicate non-random organization or evidence of systematic improvement across cosmic time. Some studies have claimed to identify anomalous correlations in galaxy distributions or cosmic microwave background patterns that could reflect optimization effects. However, these claimed detections remain highly controversial, with most analyses finding that observed patterns are consistent with standard models of cosmic evolution driven by gravitational dynamics and quantum fluctuations. The challenge lies in distinguishing genuine optimization signatures from the natural tendency of gravitational systems to self-organize into complex hierarchical structures. Gravity itself acts as an information processing mechanism, creating correlations and patterns that might mimic the signatures of more exotic optimization processes. Advanced machine learning techniques are now being applied to cosmic data in attempts to identify subtle optimization signatures that human analysis might miss. These algorithms can process vast quantities of observational data, searching for patterns that indicate systematic deviations from random cosmic evolution. The results of these machine learning analyses have been intriguing but inconclusive. Some algorithms identify statistical anomalies in cosmic data that could indicate optimization effects, while others find no evidence for deviations from standard cosmological models. The interpretation of these results requires careful consideration of potential systematic biases in both the data and the analysis methods. The development of next-generation observational facilities promises to provide unprecedented precision in cosmic measurements, potentially resolving these ambiguities through sheer statistical power. The Vera Rubin Observatory will catalogue billions of galaxies across cosmic time, while space-based missions like Euclid and the Nancy Grace Roman Space Telescope will measure cosmic expansion and structure formation with extraordinary accuracy. These observations will test recycling theories through multiple independent channels. Measurements of dark energy evolution, gravitational wave backgrounds, primordial nucleosynthesis patterns, and large-scale structure statistics will all constrain the possible mechanisms through which cosmic cycling might operate. The convergence of evidence from multiple observational channels could finally provide the definitive tests that recycling theories require. If cosmic cycling is real, its signatures should appear consistently across different types of measurements, creating a coherent picture that supports specific theoretical frameworks. Conversely, if recycling theories make predictions that fail to match high-precision observations, this negative evidence would significantly constrain the possible mechanisms through which cosmic cycling might occur. Science advances through both confirmation and refutation, and definitive negative results would be as valuable as positive detections. The stakes in this observational campaign extend far beyond academic cosmology into the deepest questions about the nature of existence itself. Understanding whether the universe recycles would fundamentally alter human perspectives on time, meaning, and our place in cosmic history. If cosmic recycling proves real, it would suggest that consciousness participates in processes that transcend individual mortality, connecting our brief existence to eternal cycles of cosmic creativity. Our thoughts, dreams, and achievements would become part of an infinite cosmic story where endings become beginnings, across scales that dwarf human comprehension. If recycling proves false, consciousness emerges as a temporary flowering of complexity destined for ultimate extinction when the universe reaches its final thermal equilibrium. This perspective demands that we find meaning and purpose within the finite span of cosmic evolution, accepting that all achievements of intelligence will eventually vanish into the cold emptiness of heat death. The scientific resolution of cosmic recycling thus carries implications that ripple through every domain of human understanding. Philosophy, religion, art, and ethics all depend implicitly on assumptions about the ultimate nature of time and existence that cosmic recycling research could fundamentally challenge or confirm. We stand at an extraordinary moment in the history of human knowledge, where our observational capabilities are approaching the precision needed to answer questions that have puzzled thinking beings since consciousness first emerged in the cosmos. The universe has spent nearly 14 billion years evolving the complexity necessary to ask questions about its own ultimate fate. Through us, the cosmos has developed the capacity to wonder whether its story has an ending or continues forever through mechanisms of renewal that transcend our current understanding. We are the universe becoming conscious of its own potential for death and rebirth, using the tools of mathematics and observation to probe the deepest mysteries of existence. The answers we discover in the coming decades will shape human culture for generations to come, providing the scientific foundation for new philosophies of existence that incorporate our growing understanding of cosmic processes. Whether the universe dies once or lives forever, the very act of asking these questions represents an extraordinary achievement of cosmic evolution. The quantum vacuum continues its eternal dance of creation and annihilation around us, indifferent to our attempts to understand its deeper significance. Virtual particles appear and vanish in accordance with mathematical laws that permit no exceptions, following principles that operate on scales from the subatomic to the cosmic. Yet within this dance of quantum possibilities lies the potential for cosmic renewal through mechanisms we are only beginning to comprehend. The same quantum processes that stabilize atoms and enable chemistry might also provide pathways for entire universes to tunnel between different states of existence, creating cycles of cosmic death and rebirth that dwarf our current conceptual frameworks. The mathematics of quantum cosmology reveals that the boundary between existence and non-existence becomes fluid when viewed from the proper perspective. What appears to be ultimate termination from one viewpoint might represent transformation and renewal from another, suggesting that even the most definitive cosmic endings might not be final. These quantum perspectives on cosmic recycling challenge our deepest intuitions about time, causality, and the nature of existence itself. We are forced to consider possibilities that stretch the limits of human comprehension, where universes tunnel into existence from nothing and consciousness emerges from the quantum foam of space-time itself. The implications ripple outward from cosmology into every domain of human understanding, forcing us to reconsider what it means to exist in a universe that might be far stranger and more resilient than we ever imagined. The cold equations of physics become poetry when they describe processes of cosmic death and rebirth that operate across scales of time and space that transcend human experience. As we continue this journey into the deepest mysteries of existence, we carry with us the accumulated wisdom of centuries of scientific investigation. Each observation, each theoretical insight, each mathematical breakthrough adds another piece to the vast puzzle of cosmic understanding that humanity is collectively assembling. The universe has given us the extraordinary privilege of consciousness, the capacity to wonder about our own origins and ultimate destiny. Through us, the cosmos contemplates its own potential for eternal existence or final termination, using the tools of reason and observation to probe questions that define the very meaning of existence itself. The story continues to unfold in laboratories and observatories around the world, where dedicated researchers push against the boundaries of human knowledge in search of answers to the most profound questions ever asked. Whether the universe dies once or lives forever, our quest to understand these cosmic processes represents one of the greatest adventures in the history of consciousness. The mathematics underlying cosmic recycling theories has reached extraordinary levels of sophistication, incorporating insights from quantum field theory, general relativity, string theory, and statistical mechanics in frameworks that would have seemed like pure fantasy to scientists just decades ago. These equations describe processes so fundamental that they govern the very existence of space and time itself. Within these mathematical structures lie hidden the secrets of cosmic longevity or mortality, encoded in relationships between energy, entropy, and the quantum geometry of space-time. The solutions to these equations will ultimately determine whether consciousness represents a temporary accident in an otherwise lifeless cosmos, or an eternal feature of reality that emerges repeatedly through cycles of cosmic renewal. The precision required to distinguish between these possibilities pushes our observational capabilities to their absolute limits, demanding measurements of cosmic parameters with accuracies approaching fundamental quantum mechanical bounds. We are attempting to detect signals that might have traveled across multiple cosmic cycles, carrying information about processes that occurred before the Big Bang. Each new observation adds weight to one side or another of this cosmic balance, gradually tilting our understanding toward heat death or eternal recycling. The universe itself serves as our laboratory, providing the only experimental apparatus capable of testing theories about cosmic-scale processes. The data streams in from telescopes scattered across the globe and throughout the solar system, each measurement carrying the potential to revolutionize our understanding of cosmic destiny. Temperature fluctuations in the cosmic microwave background, gravitational wave signatures from the quantum vacuum, subtle variations in the expansion rate of space itself all contribute to our growing comprehension of cosmic recycling possibilities. The analysis of this data requires computational resources that strain the limits of current technology, processing petabytes of information through algorithms designed to extract the faintest possible signals from noise that threatens to overwhelm any genuine cosmic signatures. Yet within this ocean of data lie the answers to questions that have haunted human consciousness since our species first developed the capacity to wonder about ultimate things. The universe has provided us with all the information we need to understand its own fate, encoded in observations that demand only the intelligence and persistence to decode their meaning. As we stand on the threshold of potentially answering these ultimate questions about cosmic destiny, we find ourselves participants in a story that began with the first quantum fluctuations in the primordial vacuum and might continue through infinite cycles of cosmic death and renewal. The next chapter of this story is being written through our observations and calculations, our theoretical insights and experimental discoveries. The universe watches through our eyes as we unravel the mysteries of its own potential for eternal existence, using consciousness as its tool for understanding the deepest principles that govern reality itself. Whether we are witnessing the universe's first and only attempt at self-understanding, or participating in an eternal cycle of cosmic awakening, our role in this cosmic drama represents one of the most extraordinary developments in the history of existence. The mathematical precision required to test these theories pushes us into realms where the distinction between theoretical prediction and experimental verification becomes extraordinarily subtle. When we examine the cosmic microwave background radiation with instruments like the Planck satellite, we're analyzing photons that have traveled for over 13 billion years, carrying within their wavelength patterns the fossil evidence of whatever processes shaped the earliest moments of cosmic history. These ancient photons reveal temperature fluctuations of just a few millionths of a degree, variations so tiny that detecting them requires cooling our instruments to temperatures colder than the depths of interstellar space. Yet within these minute temperature differences lies encoded the entire history of how matter first began to clump together under gravitational attraction, eventually forming the cosmic web of galaxies we observe today. The statistical analysis of these temperature patterns provides one of our most powerful tools for distinguishing between different models of cosmic evolution. If the universe underwent a big bounce rather than emerging from a true singularity, the compression and expansion phases would leave distinctive fingerprints in these primordial fluctuations. Computer simulations of bouncing cosmologies predict specific correlations in the cosmic microwave background that differ subtly but measurably from those expected in standard Big Bang models. The challenge lies in achieving sufficient observational precision to detect these differences, which often amount to statistical variations of just a few percent across the entire sky. Recent advances in data analysis techniques have begun to approach this level of sensitivity. Machine learning algorithms trained on thousands of simulated cosmic histories can now identify patterns in observational data that human analysts might miss entirely. These artificial intelligence systems process the complete statistical structure of cosmic microwave background measurements, searching for the subtle signatures that could distinguish between competing theories of cosmic origin. The results of these analyses remain tantalizingly inconclusive. Some algorithms identify weak statistical preferences for bouncing cosmologies, while others find no significant deviations from standard Big Bang predictions. The interpretation of these results requires extraordinary care, as the human tendency to perceive meaningful patterns in random data becomes particularly problematic when searching for signals at the edge of detectability. The challenge of cosmic recycling detection extends beyond the cosmic microwave background into the realm of gravitational wave astronomy. The ripples in space-time discovered by LIGO and Virgo carry information about the most violent events in cosmic history, but they also provide a window into the fundamental properties of space and time themselves. If our universe emerged from a quantum bounce, the transition from contraction to expansion would have generated gravitational waves across all frequency ranges. These primordial gravitational waves would propagate through space for billions of years, creating a background signal that permeates the entire cosmos. The detection of this gravitational wave background represents one of the holy grails of observational cosmology. Current instruments lack the sensitivity to measure these ultra-low frequency signals, but planned space-based observatories could achieve the precision needed to probe this cosmic relic radiation. The European Space Agency's Laser Interferometer Space Antenna mission will deploy 3 spacecraft in a triangular formation, millions of kilometers apart, creating a gravitational wave detector of unprecedented sensitivity. This space-based observatory will be capable of measuring distance changes smaller than 1,000th the width of an atomic nucleus across baselines comparable to the diameter of Earth's orbit. If successful, LISA could potentially detect the gravitational wave echoes of cosmic bouncing events, providing the first direct observational evidence for recycling mechanisms operating on cosmic scales. The absence of such signals would be equally informative, ruling out entire classes of bouncing cosmologies and constraining the possible mechanisms through which cosmic cycling might occur. The search for gravitational wave signatures of cosmic recycling illustrates a broader challenge in modern cosmology: the need to extract information about cosmic scale processes from observations that necessarily sample only tiny fractions of space and time. We're attempting to understand the behavior of an infinite universe based on measurements confined to our local cosmic neighborhood. This observational limitation becomes particularly acute when considering theories that predict cosmic recycling on timescales vastly longer than the current age of the universe. If cyclic processes operate with periods of trillions of years, we might be observing our cosmos during a brief moment within a much longer cycle, making it extremely difficult to detect the underlying periodicity. The statistical mechanics of cosmic recycling provide another avenue for theoretical investigation that doesn't depend on direct observation of cycling events. The second law of thermodynamics, which governs the irreversible increase of entropy in isolated systems, places fundamental constraints on any proposed recycling mechanism. Classical thermodynamics suggests that each cosmic cycle would necessarily accumulate more disorder than the previous one, gradually degrading the universe's capacity to organize itself into complex structures. This entropy problem doomed early oscillating universe models, which could not explain how thermal equilibrium might be avoided across multiple cycles. Modern approaches to cosmic recycling attempt to circumvent this difficulty through various mechanisms that could reset or redistribute entropy between cycles. The expansion of space itself during cosmic inflation could dilute entropy to negligible levels, effectively erasing the thermal history of previous cycles and allowing fresh organization to emerge. Alternative proposals invoke quantum mechanical processes that could violate classical thermodynamic constraints under extreme conditions. When matter reaches densities approaching the Planck scale, quantum gravitational effects might permit entropy reduction through mechanisms that have no analogue in ordinary thermodynamics. The mathematical framework of black hole thermodynamics provides crucial insights into these quantum entropy processes. Stephen Hawking's discovery that black holes possess temperature and entropy revealed deep connections between gravity, quantum mechanics, and information theory that continue to influence our understanding of cosmic recycling possibilities. If black holes can evaporate completely through Hawking radiation, they provide a mechanism for the universe to eliminate high entropy regions over extremely long timescales. The mathematics of this evaporation process shows that information about the matter that formed the black hole might be preserved in subtle correlations within the emitted radiation. This information preservation during black hole evaporation could play a crucial role in cosmic recycling by allowing the universe to retain memory of its organizational achievements even after apparent thermal equilibrium. The quantum information that describes complex structures might survive in encoded form, potentially influencing the development of subsequent cosmic cycles. Recent theoretical work on the black hole information paradox has revealed that the preservation and retrieval of quantum information during gravitational collapse involves extraordinarily subtle quantum mechanical processes. The mathematics suggests that information might be preserved through quantum entanglement networks that connect the interior and exterior of black holes in ways that classical physics cannot describe. Applied to cosmic recycling, these quantum entanglement mechanisms could provide channels through which information about previous cosmic cycles influences the structure of subsequent iterations. The strength and character of these influences would depend on the detailed dynamics of whatever transition process connects different cosmic epochs. The holographic principle, which emerged from studies of black hole physics, suggests that all information in a volume of space can be encoded on its boundary. This principle implies that three-dimensional reality might actually be a projection from information stored on a two-dimensional surface, fundamentally altering our understanding of space, time, and information. In cosmological contexts, holographic encoding could allow complete information about cosmic cycles to be preserved in the quantum geometry of space-time boundaries. Even if the interior of a cosmic volume undergoes complete thermalization, the boundary conditions might retain sufficient information to seed the structure of future cycles. The mathematical implementation of holographic cosmology reveals that the information storage capacity of cosmic boundaries scales with area rather than volume. This scaling relationship ensures that even universes of arbitrary size can have their complete state holographically encoded in finite boundary regions. The retrieval of this encoded information during cosmic transitions would require physical processes operating at the intersection of quantum mechanics and general relativity. Current research in quantum gravity provides specific mechanisms for such information transfer, operating through quantum entanglement networks that connect boundary and interior degrees of freedom. These holographic information storage and retrieval mechanisms could explain how cosmic recycling maintains structural coherence despite the enormous energies and complex dynamics involved in cosmic transitions. The holographic encoding would automatically protect crucial information patterns while allowing non-essential details to be gradually erased. The emergence of quantum error correction in holographic systems adds another layer of sophistication to these information preservation mechanisms. Just as quantum computers use error correction codes to maintain coherent information despite environmental noise, cosmic holographic systems might naturally implement protocols that preserve essential information across multiple recycling events. This quantum error correction could explain how recycling mechanisms maintain their effectiveness over multiple cosmic cycles, gradually optimizing their ability to preserve and transmit the information patterns that enable complex structure formation. The universe would essentially learn to recycle more effectively through repeated iterations. The possibility that cosmic recycling involves optimization processes raises profound questions about the relationship between physics and information processing on cosmic scales. If the universe can improve its recycling efficiency through experience, this suggests that cosmos possess computational capabilities that far exceed any conceivable artificial system. Information theoretic analyses of cosmic evolution reveal that the universe processes and stores information through gravitational dynamics, stellar nucleosynthesis, and quantum mechanical processes operating across all scales simultaneously. The computational resources available to cosmic systems dwarf human technology by incomprehensible margins. If these resources can be organized through recycling processes to implement learning and optimization algorithms, the resulting information processing capabilities could guide cosmic evolution toward configurations that maximize the universe's capacity for complexity and consciousness. The search for evidence of such cosmic optimization has become a subtle theme in observational cosmology. Researchers examine the statistical properties of galaxy formation, stellar evolution, and large-scale structure development, looking for patterns that might indicate systematic improvement in the universe's organizational capabilities over cosmic time. Some studies have identified correlations in cosmic structure formation that could reflect optimization effects, though these remain highly controversial. The challenge lies in distinguishing genuine optimization signatures from the natural tendency of gravitational systems to self-organize through purely physical processes. The application of machine learning techniques to cosmic data analysis has revealed intriguing patterns that might indicate non-random organization in cosmic evolution. These algorithms can process vast quantities of observational data, identifying subtle correlations that human analysis might overlook entirely. However, the interpretation of these algorithmic discoveries requires extreme caution. Machine learning systems excel at finding patterns in data, but they can also identify spurious correlations that have no physical significance. Distinguishing genuine cosmic optimization signatures from algorithmic artifacts remains an ongoing challenge. The theoretical framework of eternal inflation provides a different perspective on cosmic recycling that operates through spatial rather than temporal mechanisms. In this model, quantum fluctuations in primordial scalar fields create regions where space undergoes exponential expansion, continuously generating new pocket universes with different physical properties. Each inflationary bubble experiences its own Big Bang and subsequent evolution, creating a vast ensemble of universes with every possible combination of physical parameters. Conscious observers would naturally find themselves in bubbles where the physics permits their existence, explaining the apparent fine-tuning of our cosmic environment. This spatial multiverse scenario makes dramatically different predictions than temporal recycling theories. Instead of cyclical repetition within a single universe, eternal inflation generates infinite diversity across infinite space, with every possible cosmic history playing out simultaneously in different regions. The observational signatures predicted by eternal inflation differ substantially from those expected in temporal recycling models. Inflation theories make specific predictions about temperature and polarization patterns in the cosmic microwave background that result from quantum fluctuations during the inflationary epoch. These predictions have been confirmed by multiple independent observations, providing strong support for some version of inflationary cosmology. However, the eternal nature of inflation remains more speculative, as it requires extrapolating successful local physics to cosmic scales where direct testing becomes impossible. The measure problem in eternal inflation represents one of the most challenging conceptual issues in modern cosmology. If infinite universes with every possible physical configuration are constantly being created, traditional methods for calculating probabilities break down completely. Recent work in quantum cosmology has attempted to address these foundational issues by developing new frameworks for understanding cosmic creation processes. These approaches suggest that universe formation might not be random but governed by deeper principles that determine which types of cosmos are more likely to emerge and persist. The quantum genesis model represents one such attempt to provide a principled approach to cosmic creation that avoids the mathematical pathologies of simpler models. This framework proposes that universes are created in symmetric pairs through quantum mechanical processes, naturally resolving many of the conceptual difficulties that plague other creation scenarios. If quantum genesis proves correct, the apparent fine-tuning of our universe would result not from random chance or infinite repetition, but from fundamental symmetries in the quantum processes that govern cosmic creation. The relationship between universe and anti-universe pairs could determine physical constants through entanglement effects that persist across cosmic evolution. These competing theoretical frameworks reflect deeper philosophical divisions within the physics community about the nature of scientific explanation itself. Some researchers prefer theories that make minimal assumptions about unobservable phenomena, even if this requires accepting apparently improbable features of the observed universe. Others argue that cosmic fine-tuning demands explanation through mechanisms that transcend our local cosmic environment, whether through temporal recycling, spatial multiverses, or quantum creation symmetries. The resolution of these debates may require observational breakthroughs that provide definitive tests of competing theoretical frameworks. The development of next-generation observational facilities promises unprecedented precision in cosmic measurements that could finally distinguish between different models of cosmic origin and evolution. The James Webb Space Telescope has already begun providing extraordinarily detailed observations of the early universe, revealing galaxy formation processes occurring just hundreds of millions of years after the Big Bang. Future missions will push even further into cosmic history, potentially observing the first stars and galaxies to form after cosmic recycling events, or Big Bang nucleosynthesis. The statistical properties of these primordial structures could reveal whether our universe emerged from a quantum bounce, inflationary expansion, or some other creation mechanism. Ground-based observatories are also approaching unprecedented sensitivity for detecting subtle signals that could indicate cosmic recycling. The Vera Rubin Observatory will catalogue billions of galaxies across cosmic time, while advanced gravitational wave detectors will probe space-time dynamics with exquisite precision. The convergence of evidence from multiple observational channels could provide the definitive tests that recycling theories require. If cosmic cycling operates through any of the proposed mechanisms, its signatures should appear consistently across different types of measurements, creating a coherent observational picture. Conversely, if recycling theories make predictions that fail to match high-precision observations, these negative results would significantly constrain the possible mechanisms through which cosmic cycling might occur. The power of science lies in its ability to eliminate incorrect theories through careful observation and analysis. The implications of resolving the cosmic recycling question extend far beyond academic physics into fundamental questions about the nature of existence, consciousness, and meaning within cosmic history. Understanding whether the universe undergoes cycles of death and renewal would transform human perspectives on time, purpose, and our place in the cosmic order. If recycling proves real, consciousness becomes part of an eternal cosmic story, where apparent endings become new beginnings across scales that transcend individual experience. Our thoughts, achievements, and creative expressions would participate in processes that connect finite lives to infinite cosmic creativity. If recycling proves false, consciousness emerges as a temporary flowering of complexity destined for ultimate extinction when the universe reaches its final thermal equilibrium. This perspective demands that we find meaning and purpose within the finite span of cosmic evolution. The scientific resolution of these questions would provide the empirical foundation for new philosophical frameworks that incorporate our growing understanding of cosmic processes. Whether the universe dies once or lives forever, the very capacity to investigate these questions represents an extraordinary achievement of cosmic evolution. Through our observations and calculations, the universe has developed the ability to contemplate its own ultimate fate. Using consciousness as a tool for understanding the deepest principles that govern reality itself. We are the cosmos becoming aware of its own potential for eternal existence or final termination. The quantum vacuum continues its eternal fluctuations around us, indifferent to our attempts to decode its deeper significance. Yet within this dance of virtual particles and field oscillations lie the mechanisms that could either terminate all organized complexity forever or provide pathways for infinite cosmic renewal. The mathematics of quantum field theory reveals that even perfect vacuum contains infinite energy in its ground state fluctuations. This zero-point energy might seem like a mere theoretical artifact, but it could play a crucial role in cosmic recycling through processes that violate classical energy conservation on cosmic scales. Quantum tunneling events in the primordial vacuum could theoretically create regions of space with sufficient energy density to undergo cosmic inflation, essentially birthing new Big Bang events from apparent nothingness. The probability of such spontaneous creation is unimaginably small, but infinity provides unlimited opportunities for even the most unlikely quantum processes to occur. These quantum creation scenarios suggest that heat death might not represent the absolute end of cosmic possibility, but merely a transition to a regime where quantum fluctuations operate unopposed by thermal processes. In the cold emptiness of a heat-dead universe, quantum tunneling could eventually generate new regions of spacetime that undergo explosive expansion. The timescales involved in such quantum resurrection processes exceed human comprehension by vast margins. Current calculations suggest that spontaneous Big Bang creation through vacuum tunneling would require roughly 10 to the power of 10 to the power of 56 years to become probable. This temporal scale dwarfs not only human history, but the entire thermal lifetime of ordinary matter. By the time quantum tunneling creates new universes, every atom in our current cosmos would have decayed into elementary particles through processes that operate on merely astronomical timescales. Yet from the perspective of eternal time, even these incomprehensible delays become insignificant. If time itself is infinite, then any process with non-zero probability will eventually occur, no matter how unlikely it might seem from our limited temporal perspective. The quantum mechanical basis for cosmic creation through vacuum tunneling rests on the same principles that govern radioactive decay and other familiar quantum processes. The mathematical framework of quantum field theory provides specific calculational methods for determining tunneling rates across potential energy barriers of cosmic proportions. These calculations reveal that the most probable new universes would emerge with the smallest possible initial size and the highest vacuum energy density. Such baby universes would immediately undergo exponential expansion due to their enormous energy content, rapidly growing to macroscopic scales through inflationary dynamics. The initial conditions of these quantum-created universes would bear no relationship to the thermal equilibrium state from which they emerged. Each spontaneous creation event would essentially reset cosmic evolution, providing fresh opportunities for structure formation, complexity development, and potentially the emergence of new forms of consciousness. This quantum approach to cosmic recycling avoids many of the conceptual difficulties that plague classical cyclic models. Instead of requiring the physical contraction and re-expansion of existing space, new universes emerge through purely quantum mechanical processes that can operate even during continued expansion of the parent cosmos. The entropy problems that doomed earlier cyclic theories become irrelevant when new universes are created rather than recycled. Each quantum tunneling event produces a genuinely fresh cosmos with minimal initial entropy, allowing complex organization to develop without carrying forward the thermal baggage of previous cosmic epochs. However, the observational consequences of quantum cosmic creation remain extremely limited. The parent universe would show no detectable signs of spawning new cosmos through vacuum tunneling, as these creation events would occur in causally disconnected regions of spacetime. From our perspective within a potentially heat-dead universe, the quantum creation of new cosmos would be completely unobservable. We could never directly verify that cosmic recycling through quantum tunneling actually occurs, even if the mathematical predictions prove correct. This observational isolation highlights a fundamental limitation in our ability to test theories about cosmic recycling. The most promising mechanisms for cosmic renewal operate on scales of time and space that transcend any conceivable observational capability. We are forced to rely on mathematical consistency, theoretical elegance, and indirect observational constraints to evaluate recycling proposals. The universe itself becomes our only laboratory for testing ideas about cosmic scale processes. The philosophical implications of quantum cosmic creation extend into deep questions about the relationship between mathematics and physical reality. If universes can tunnel into existence from pure quantum vacuum, what distinguishes mathematical possibility from physical actuality? The quantum creation scenario suggests that existence might be far more prolific than our everyday experience indicates. If vacuum tunneling can generate universes with arbitrary physical properties, then reality might encompass infinite variations on cosmic themes we haven't even imagined. This proliferation of possible universes through quantum creation mechanisms connects to broader questions about the nature of physical law itself. Are the constants and equations that govern our cosmic environment fundamental features of reality, or merely local properties of our particular quantum creation event? Recent work in string theory and quantum gravity suggests that physical laws might be much more flexible than previously imagined. The fundamental constants of physics could vary between different vacuum states, creating universes with radically different properties depending on the specific quantum tunneling process that created them. If true, this variability would transform cosmic recycling from simple repetition into infinite exploration of physical possibility. Each quantum creation event would potentially discover new ways for matter and energy to organize themselves, gradually mapping out the full landscape of possible physics. The mathematical framework describing this landscape of possibilities reveals structure and patterns that might guide cosmic evolution toward increasingly interesting configurations. Some regions of the landscape might be more accessible through quantum tunneling, creating statistical preferences for certain types of universe over others. These preferences could explain apparent fine-tuning in our observed cosmos, without requiring special initial conditions or anthropic selection effects. If quantum tunneling naturally favors universes with particular combinations of physical constants, we would expect to find ourselves in a cosmos that exhibits these favored characteristics. The investigation of quantum cosmic creation has thus evolved into a search for deeper principles that might govern the statistical properties of universe formation. Researchers explore mathematical structures that could determine which types of cosmos are more likely to emerge through quantum processes. This theoretical work operates at the intersection of quantum field theory, general relativity, and information theory, requiring mathematical tools that push the boundaries of current theoretical physics. The equations describing quantum cosmic creation involve path integrals over infinite dimensional spaces of possible geometries and field configurations. Solving these equations requires approximation methods and numerical techniques that strain the capabilities of current computational resources. Even the most sophisticated computer simulations can only explore tiny regions of the vast mathematical landscape that describes possible cosmic creation scenarios. Despite these computational limitations, theoretical investigations have revealed surprising structure in the quantum creation process. Certain types of universe appear to be strongly favored by the fundamental mathematics, while others seem to be suppressed by quantum mechanical effects. These mathematical preferences could provide the explanation for cosmic fine-tuning that has eluded physicists for decades. Instead of requiring special initial conditions or anthropic reasoning, the apparent optimization of our universe for complexity might reflect deep principles governing quantum cosmic creation. The search for such principles has become one of the most active areas of theoretical cosmology, connecting fundamental questions about quantum gravity to practical issues in observational astronomy. Understanding why our universe exhibits its particular properties could provide crucial insights into the nature of cosmic recycling and renewal. As we continue this investigation into the deepest mechanisms of cosmic existence, we find ourselves probing questions that stretch human conceptual abilities to their limits. The mathematical frameworks we use to describe quantum cosmic creation operate in realms where ordinary intuitions about time, space, and causality completely break down. Yet within these abstract mathematical structures may lie the keys to understanding whether consciousness represents a temporary accident in cosmic history or an inevitable feature of reality that emerges repeatedly through cycles of quantum creation and renewal. The universe has provided us with the intellectual tools needed to investigate its own ultimate nature. The next phase of cosmic recycling research will require unprecedented collaboration between theorists developing mathematical frameworks and observers pushing the boundaries of measurement precision. Only through this combination of theoretical insight and empirical investigation can we hope to resolve the fundamental questions about cosmic death and renewal that have driven this exploration. The stakes in this scientific endeavour extend far beyond academic achievement into the deepest questions about meaning and purpose in existence itself. Understanding whether the universe undergoes cycles of death and rebirth would transform human perspectives on time, consciousness, and our place in the cosmic story that began nearly 14 billion years ago and might continue forever through mechanisms we are only beginning to comprehend. Tonight, as we reach the culmination of our cosmic journey, we must confront the most profound realization of all. The universe we inhabit may not be heading toward a single, definitive ending. Instead, the cosmos itself might possess mechanisms so elegant and fundamental that death becomes merely another form of transformation. The evidence emerging from laboratories around the world suggests something extraordinary about the nature of vacuum itself. When physicists at CERN measure the properties of the Higgs field, they discover that our universe exists in what appears to be a metastable state. We live balanced on an energy landscape where stability and instability meet in ways that could determine the ultimate fate of everything. The measurements are precise but unsettling. The mass of the Higgs boson, combined with what we know about the top quark, places our cosmos in a region where quantum tunneling could theoretically trigger a cascade of vacuum decay. A bubble of true vacuum could nucleate spontaneously somewhere in space, expanding at light speed and rewriting the fundamental laws of physics as it grows. This possibility represents more than academic speculation. The mathematics of quantum field theory predicts that if our vacuum state is indeed false, the transition to true vacuum becomes inevitable given sufficient time. The probability might be vanishingly small on human timescales, but eternity provides unlimited opportunities for even the most unlikely quantum events to occur. Yet this apparent cosmic fragility might actually be evidence of something far more profound. Recent calculations in quantum cosmology suggest that vacuum decay events don't necessarily destroy universes, but could transform them into entirely new configurations of space and time. The bubble of altered physics expanding at light speed might not represent cosmic death, but cosmic metamorphosis. The mathematical framework describing these vacuum transitions reveals deep connections between quantum mechanics and the geometry of space-time itself. When physicists solve the equations governing bubble nucleation in curved space, they discover that the process resembles cosmic inflation operating in reverse. The expansion of true vacuum through false vacuum creates conditions remarkably similar to those that drove the original inflationary epoch. This similarity is not coincidental. The same quantum fields that powered cosmic inflation in our universe's earliest moments continue to permeate space today, maintaining the potential for new inflationary events whenever vacuum decay occurs. Each bubble of true vacuum could serve as the seed for explosive expansion, creating fresh regions of space-time where entirely new cosmic histories could unfold. The implications transform our understanding of cosmic death from termination to renewal. Instead of representing the absolute end of physical possibility, vacuum decay becomes a mechanism for cosmic reproduction. Our universe might be just one bubble in an infinite foam of cosmic creation, where apparent endings become beginnings. Through quantum processes we are only beginning to comprehend. Observational cosmology provides tantalizing hints that such processes might already be operating in regions of space beyond our current observational horizon. The cosmic microwave background radiation carries subtle statistical signatures that some researchers interpret as evidence of bubble collisions occurring during cosmic inflation. These collision signatures would appear as circular patterns in the temperature fluctuations of the cosmic microwave background, created when expanding bubbles of space encountered each other during the inflationary epoch. Multiple research groups have claimed to identify such patterns in high-precision cosmic data, though the statistical significance remains hotly debated. The controversy surrounding these observations reflects the extraordinary difficulty of detecting evidence for cosmic recycling mechanisms that operate on scales far exceeding our observable universe. We are attempting to infer the existence of cosmic processes from their subtle influence on phenomena we can actually measure. The challenge becomes even more complex when we consider that successful cosmic recycling might deliberately erase most traces of previous cosmic cycles. The inflationary expansion that could follow vacuum decay events would stretch space so dramatically that any information about pre-existing cosmic structure would be diluted beyond detection. This information erasure provides a natural solution to the entropy problem that plagued earlier cyclic models. Instead of requiring mechanisms to reset thermodynamic equilibrium, vacuum decay creates genuinely new regions of spacetime that begin with minimal entropy. Each cosmic cycle starts fresh, unencumbered by the thermal history of previous iterations. The mathematical elegance of this recycling mechanism has attracted serious attention from theoretical physicists working at the intersection of quantum field theory and cosmology. The same equations that describe particle physics in laboratory experiments extend naturally to cosmic scales, suggesting that universe creation through vacuum decay represents a direct application of established physical principles. Computer simulations of vacuum decay in expanding spacetime have revealed remarkable richness in the possible outcomes of such events. Depending on the detailed properties of the quantum fields involved, vacuum decay can produce bubbles that expand, contract, or undergo complex oscillatory behavior that defies simple classification. Some decay scenarios generate multiple bubbles simultaneously, creating networks of interconnected cosmic regions that exchange matter and energy through quantum tunneling processes. These bubble networks could support forms of cosmic recycling that involve communication and interaction between different cosmic domains. Other decay pathways lead to the formation of baby universes that pinch off completely from their parent cosmos, evolving independently according to physical laws that might differ dramatically from those governing our observable universe. These disconnected cosmic offspring would be causally isolated from their point of origin, free to explore entirely different evolutionary trajectories. The diversity of possible outcomes reflects the fundamental flexibility of quantum field theory when applied to cosmic scales. The mathematical framework that successfully describes particle interactions in accelerator experiments naturally accommodates universe creation, cosmic recycling, and forms of cosmic reproduction that challenge our most basic assumptions about the nature of existence. This theoretical richness has motivated efforts to develop observational tests that could distinguish between different vacuum decay scenarios. If our universe is embedded within a larger structure of bubble universes created through vacuum decay, this cosmic environment might leave detectable signatures in phenomena we can actually observe. Gravitational wave astronomy provides one promising avenue for such investigations. The collision between expanding vacuum bubbles would generate gravitational waves across all frequency ranges, creating a stochastic background that could persist for billions of years after the original collision events. Tonight, as we reach the end of our cosmic journey through time and possibility, we find ourselves standing at the threshold of one of science's most profound questions. The universe that gave birth to stars and planets, to life and consciousness, to the very capacity for wonder itself, might not be racing toward a final ending after all. The equations of quantum mechanics whisper of resurrection through vacuum tunneling. The mathematics of string theory suggests endless collisions between cosmic brains. Loop quantum gravity points toward bounces that could preserve the memory of previous cosmic cycles across unimaginable spans of time. Whether the universe dies once in the cold emptiness of heat death, tears itself apart in the violence of a big rip, or finds ways to begin again through mechanisms we are only beginning to understand, one thing remains certain. We are living witnesses to the cosmos contemplating its own mortality and potential for renewal. The answers to these ultimate questions lie hidden in the cosmic microwave background radiation, in gravitational waves rippling through space-time, in the quantum fluctuations of empty space itself. Each new observation brings us closer to understanding whether consciousness represents a temporary flowering of cosmic complexity or an eternal feature of reality that emerges again and again across infinite cycles of death and rebirth. The universe has given us the extraordinary gift of awareness, the capacity to ask these questions that define existence itself, and perhaps, in seeking these answers, we become the cosmos learning to transcend its own apparent limitations.